then when you compute the derivative, what you do is actually you look at another function which is defined by looking at the incremental ratio f of x minus f of x naught, x minus x naught, right? So it's like you construct a new function which is in principle is not which is not defined at x naught, right? The formula doesn't define anything at x naught. So you're actually taking the function phi of x given by f of x minus f of x naught divided by x minus x naught. So that's a new function, and this object is just defined by the formula that I gave, is just defined for x different from x naught. Okay? I don't know, in this case probably doesn't even look too much like that. Okay? I mean, it's just a picture for the sake of drawing a picture. Don't look too much at what I know. It doesn't pretend to be the incremental ratios of both subsets, okay? But it should be. And so here you see very well why in the definition of limit, right? So what does it mean that the limit exists over there? Well, of course, if it exists, you call it so this limit is denoted by f prime at x naught, right? This is very well known. So you have this limit. What does it mean that this limit exists? So if you want to write it down explicitly, it means that for every epsilon positive, there exists some delta positive such that if x minus x naught is less than delta, and x is a point inside the interval I, of course, then your function phi of x, so the incremental ratio of f, it's the distance from the incremental ratio from this constant value, this limit, this derivative, is less than this, right? So as you see why in the definition of limit we have stressed the fact that when you take a limit, you don't really need to know the function you're taking the limit of at the limit point, okay? And that's exactly because the definition of limit is tailored to be usable to define differentiability. And of course when you try to define differentiability, you want to, I mean, you don't know how to define the incremental ratio at x naught. That's exactly what you want to do in a sense, right? You want to extend the definition of the incremental ratio in a meaningful way to the point x naught, right? And to do that, you compute the limit. Okay.
Should we consider I as the domain of the function?
I mean, it's implicit that the function is defined. I mean, it's stated that I is something contained, is an interval contained in the domain of your function. And if the domain of your function is not an interval, it's typically a union of intervals. Okay, that's the definition, and you should be familiar with this definition, right? And you've seen it probably already or not. Starting from the definition, you can prove many of the rules of differentiation that you have been using, right? So Leibniz rule, the quotient rule, and so on. So what is the proof? What are the proofs of these basic differentiation rules? Do the exercise with the definitions of differentiability. F of x and g of x be differentiable at a point x naught inside some interval I. Okay, so rule number one if A and B are real numbers, then the derivative of, and you define a new function h of x by taking A times f of x plus B times g of x. Then h prime at x naught is just A f prime at x naught plus B g prime at x naught. So the derivative of the linear combination of functions is just the linear combination of the derivatives. Right. Then you have the Leibniz rule. If you set now h of x to be the product of f and g, then h of x is differentiable at x naught, and h prime of x naught is equal to f prime of x naught g of x naught plus f of x naught g prime of x naught. And then there is the quotient rule. Which is the following. So if say g of x naught is not 0, and you set h of x as the ratio of f and g, then h of x will be differentiable at x naught with h prime of x naught equal to f prime of x naught over g of x naught minus f of x naught over g of x naught squared times g prime of x naught. That's the usual quotient rule, right? Let's see the proofs of these three rules. So the first one, it's really simple. I mean, the first one is, it's almost nothing, but let's write it. The proof of one, start, you want to compute the limit of the geometric ratio of this function h, right? In the first case, when h is defined as a linear combination of f and g, so a and b will be numbers, so not functions, but constants. So that's the, you are familiar, right, with the quotient rule. F prime g minus g prime f over g squared. You can write it like that. It's just one of the values will improve. So the proof of one, you just write down the definition of h, right? So, and then you just get a f of x plus b g of x minus a f of x naught minus b g of x naught divided by x equal to x naught. So you just rearrange the terms. So the thing that is written here is actually equal to a times the incremental ratio of f plus b times the incremental ratio of g. just I'm just factoring out an a from the terms that are multiplied by a, and I'm factoring out a b from the two terms that are multiplied by d. So I just get that. So there's not so much happening here. So as you said, x to x naught, the incremental ratio of f at x naught converges to f prime of x naught, right? Because remember, our assumption is that f and g are both differentiable functions at point x naught, right? So once I've written the incremental ratio of my h like that, right, I can send x to x naught. So and when I compute so the limit as x goes to x naught of the incremental ratio of h, that's really now a f prime of x naught plus b g prime of x naught, right? It's simple because this guy is going here, and this guy is going here. That's prime, right?
Mm-hmm.
This is really simple. Okay. Are you on board with that? Okay. So, if you don't have questions on this first proof, let's move to the second one. So, in order to prove the second one, we need a simple remark, okay, but we need it before we enter into it. So the simple remark is that if a function is differentiable at a point, then it must be continuous at that same point. Okay? So as a consequence of the definition of differentiability, we have the following remark. So let me write down this remark before I prove second statement of this proof. And the remark is that if f of x is differentiable at a point x naught in some interval I, then f of x is continuous at x naught. Okay? And the proof of this remark, the proof is that different from x naught, we clearly have the following thing, right? We have that f of x minus f of x naught, we can clearly write it as f of x minus f of x naught divided by x minus x naught times x minus x naught, right? That's not particularly deep, but it's definitely good. Right? And if I let x go, so in particular, the limit as x goes to x naught of f of x minus f of x naught can be computed as the limit of this first factor, which is f prime, because I'm assuming my function is differentiable, right? So this will be f prime of x naught times the limit of the second factor. What is the limit of the second factor as x goes to x naught?
0.
It's 0, right? Okay. So the limit is 0. But saying that this limit is 0 exactly means that the limit as x goes to x naught of f of x is equal to f of x naught. So it means that your function is continuous, right? So there is no escape. If you ask that the function is differentiable, you are asking that you are continuous at least. That's just like this. If you want, the very simple explanation is that being differentiable means that this ratio goes somewhere to a limit, right? But you're dividing by something that goes to 0. And the only way, if you have a fraction where the denominator goes to 0, The only way for the limit to exist is that also the numerator goes to 0, right? Otherwise, if you are going to some finite number, this thing goes to plus infinity or doesn't have a limit. So the only possibility for a ratio to have a meaningful limit when the denominator goes to 0 is that also the numerator goes to 0. Otherwise, there is no hope. You are dividing something fixed in a sense by something becoming smaller and smaller. So you blow up to infinity, or you oscillate between minus infinity and plus infinity, but you definitely do not have a limit. And formally, and this is intuition, formally what I'm saying is just that, okay, write it down like that. Right? If x is different from x naught, this is a meaningful identity. And when you take the limit as x goes to x naught, you use this identity, use the fact that by assumption you are differential, so you know what this fraction does, it converges to f prime of x naught. On the other hand, you trivially know what this guy does, because it goes to 0. So that's a number, that's 0, the product is meaningful, and it's 0. Okay? So f of x goes to f of x naught, and you're necessarily continuous.
And the converse is true.
Right?
And the converse is true, right? If the function is continuous, if fx is continuous at x naught, then the function is differentiable at x naught?
No, that's false.
Okay.
But we are going to see it in a second. Okay? So the converse is not true. Okay, maybe let me say this immediately. Or maybe I will first finish the proof of this theorem. Okay, you can wait a moment to see why a continuous function is not necessarily differential. Okay, so as I said, I will leave this remark to prove Leibniz rule. Okay, so Leibniz rule uses the fact that the function in our theorem, being differentiable, will also be continuous at x naught. That's something I'm going to use in a moment. Okay, so let me prove two. You write down the incremental ratio of h. Now we have changed the definition of h, right? Now h is the product of f and g. So here I have to write something else. So in case 2, for the Leibniz rule, h of x is defined as the product of f and g, right? So what's written here is just f of x times g of x minus f of x naught times g of x naught. And this is divided by x times x naught. So, since my information is that f and g are differentiable, what I want to do is I want to make the incremental ratios of f and g to pop up in this formula, right? And in order to do that, I have to add and subtract f of x naught times g of x. Okay. Or I could do f of x times g of x naught. Both choices are good, but let's choose one. So here, from now I'm going to add and subtract, say, f of x naught times g of x. Okay, so that's what's going to happen in this equality sign. I am adding and subtracting at the numerator f of x naught times g of x. So if you do that, you have f of x g of x minus f of x naught times g of x plus f of x naught times g of x, and then what I had over there, f of x naught times g of x naught. And everything is divided by x minus x naught. So I can definitely write that. And you see, the advantage of having done that is that now I have fractions and I can factor out any incremental ratio against just a multiplicative factor, which is in the first case g of x, and in the second case f of x naught. This is just an algebraic identity. Again, I'm just rewriting an expression in another way. So what happens here next is that if you want to write one more step in the argument, is that I can write the first fraction as a g of x times f of x minus f of x naught over x minus x naught plus f of x naught times g of x minus g of x naught over x minus x naught. Now you see it clearly, right? By Leibniz rules. There's not nothing, you just write down an identity. So there is just rewriting what we had in a clever way, okay? And now this guy here has a limit, right? Because f is differential. This goes to f prime of x naught. Okay, what happens to this guy as x goes to x naught? What happens to g of x?
G of x naught,
Why?
because it's differentiable.
And does?
And that's continuous.
And does continues, okay? G is differentiable. The fact that G is differentiable doesn't tell you anything of G of x in principle. It's just telling you that this guy is going to G prime of x naught, right? That's what it tells you. But the remark is telling you that if you know that the incremental ratio is a limit, okay, then as a bonus, you actually know that G of x goes to G of x naught, because Gx naught is its limit. So we also know, but here we are using the remark, is not something that is embedded in the definition of differentiability. We are using that this thing is going to G of x naught. Okay? This comes from the remark. I mean, which is in the end is just little remark, okay? That you can do, that you can make given the definition of differentiability. But you have to do it. So, well, now it's everything is taken care of, right? So this guy goes to G of x naught. This guy goes to f prime of x naught. This guy goes nowhere. It's a constant, okay? And this is going to G prime of x naught. So the limit as x goes to x naught of the incremental ratio of the product function h is just what you were expecting. F prime of x naught, G of x naught, plus f of x naught, G prime of x naught.
How did you get the last step? I don't really see.
The limit?
Yeah.
So by assumption f is differentiable, right? So this guy goes to f prime of x naught.
Right.
G of x, since G is differentiable at x naught,
Then G of x goes to G of x.
exactly. Since it's differentiable at that point, it's continuous at x naught. What does it mean that G is continuous at x naught? If you take the limit of G of x, then this goes to G of x naught. So the product of the two goes to G of x naught times f prime of x naught, which is my first term.
Okay,
here.
okay.
And the second one is again the limit, yeah. And so you got the sum of limits. So you're using the theorem that tells you that the limit of the sum is the sum of the limits, and the product of the limits is the limit of the products, given that all the limits exist. Okay, so this is the proof of Leibniz rule. So in case you ever wondered what was the proof, it's pretty simple. I mean, it's just a matter of using the definition and in a simple way. So what about the quotient rule? Okay, the quotient rule, which is just how do you differentiate f over g, comes with a completely analogous argument. Let me show you how it goes. So can I erase this? Do you have questions?
Also, before you go on to the question, how did we use the remark in this proof?
So you see, here I have an algebraic identity, right? When I arrive here, I still have to take a single limit. So this is true even if the functions are not differential. I mean, the fact that fx, gx minus fx naught, gx naught divided by this is equal to that, this uses nothing.
Right.
You can do that for the Dirichlet function and another Dirichlet function. Okay? So it's always true. So when you start using the assumption, it's here, because here you use the assumption that f of x is differentiable at x naught, to say that if you take the limit as x goes to x naught, this object is going to be f prime of x naught. Okay? Have you understood? So
I mean, I don't really see how that directly relates to the remark.
okay, the remark, because when I write down this formula, my assumption, so the assumption of this thing is that f and g are differentiable at x naught, right? So what does it mean to be differentiable? It means that for g, it means that this thing is going to g prime of x naught.
Right.
Okay, and what does it mean on g of x?
That it's going to G of x, no?
Not the definition. The definition just tells you that a function is differentiable at a point if this thing goes to a number, which is by the definition denoted by g prime of x naught. But the definition of differentiability, so the definition of differentiability is just that there exists the limit as x goes to x naught of g of x minus g of x naught divided by x minus x naught.
Okay.
And you denote this limit by g prime. That's what it says. So when it's written in this definition, what happens to this thing? It's not, I mean, it's not in the definition, right? So the remark that we have here, the remark tells you that if a function is differentiable, then it's continuous. So once you tell me that you're differentiable,
So then you know that the limit exists for g of x.
and that it's equal to the value of g at the point x.
Okay.
Okay? So it's something you have to notice because it's not in the definition. That's it. It's not very deep, but it's just dotting the i's. Okay, with this time. Okay. So is it clear now? Can I erase it? Okay. So now let's move to the proof of 3. So now the function h will be the ratio of f and g. So proof of 3, we have h of x minus h of x naught divided by x minus x naught. Okay? And we want to consider the function h given by the ratio f of x over g of x. So if you do that, we have here f of x over g of x minus f of x naught over g of x naught divided by x minus x naught. And, well, as usual, the idea is just to give yourself a chance to see the incremental ratios popping up, right? So, what are you going to do?
Do we multiply by g of x over g of x and g of x naught over g of x naught?
You add and subtract f of x over g of x naught, say, or f of x naught over g of x, you can choose that. So you just do the same trick we did 1 second ago for the Leibniz rule, but you do it with what you have. So what's happening here is that now, so I will add and subtract f of x over g of x naught. Okay? So if I do that, what I have is f of x over g of x minus f of x over g of x naught, everything divided by x minus x naught, plus f of x over g of x naught minus f of x naught over g of x naught divided by x minus x naught. Okay? So I just added and subtracted this guy from what we had here. Okay. So when you subtract it, you have these minus these over x minus x naught plus this guy that I have to add back, and then minus this which was already there. Okay. Now it's just a bit of algebra to. So is it confusing? Okay. So. Now what happens is just do a little bit of algebra here to clean it up. So the first factor is an f of x, which is everywhere, right? So this will factor it out. So the first guy will look like an f of x, and now you see this f of x is getting to multiply 1 over g minus 1 over g of x naught divided by x minus x naught. So if I add up the fractions, okay, so I do g of x naught minus g of x divided by g of x over g of x naught. No, sorry, g of x times g of x naught, so I just do the how's it called? The common denominator. So I get here something like g of x naught, and here we find g of x naught minus g of x over x minus x naught plus. So think a moment about these. Do you agree with that? So that's just the first chunk of the thing, okay? Right? So it's just the first fraction. I just factored out the f of x, which was in common, and then I do the common divisor of this twice, right? And then you got the g of x naught here and the g of x there. So it's g of x naught minus g of x, not g of x minus g of x naught. Okay? And then I can do something completely analogous here, right? Actually simpler, because I just have to factor out 1 over g of x naught, which is there. So if I factor this out, I got 1 over g of x naught, and then I am left with something familiar, f of x minus f of x naught divided by x minus x naught, right? So the second thing is just there is a 1 over g of x naught multiplying both things, so it's just 1 over g of x naught times the incremental ratio left. So you look at these things, so far this is true for every function you may want to work with. You just need to know that g of x naught is different from 0, because you're dividing by g of x naught in a lot of places, and hopefully that g of x is different from 0 at least nearby g of x naught, right? For x close to x naught. What do you know these things? So that's a good moment, okay, before concluding the argument. That's a good moment to think again about what we are saying, what we are trying to do, why it makes sense. So let me make some space. So what we're trying to do is to define given the differentiable function. Let me cut and paste this line actually. Okay, so what we're trying to show is this statement. So if g of x naught is different from 0, and h of x is defined as f of x over g of x, then, so what we want to show is that h prime of x naught exists, and it's equal to f prime of x naught over g of x naught minus f of x naught over g of x naught squared times g prime of x naught, right? That's what we want to show. But now, why does the question make sense? But the question makes sense. So the statement makes sense. So let me do this remark. Okay, so since g of x naught is different from 0, and g of x is continuous at x naught, that's my previous remark, right? The previous remark is that since g is differentiable at x naught, then g is continuous at x naught, right? Now, the function g is different from 0 at x naught and it's continuous there. So can you take the value 0 anywhere close to x naught? So since the function g is continuous at x naught, and that x naught takes a value different from 0, is it going to be possible for the function to take infinitely many times the value 0 nearby x naught? No, because otherwise there would be a sequence, right, of points going to x naught where you take the value 0. So the only possible limit for g would be 0, and so g of x, and it would be g of x naught, and so g of x naught would be 0. So this is something we have proved, right? If a function has a positive limit, say, then there exists a delta positive such that in the delta neighborhood of the point, the function stays positive. And if the limit is negative, then there is a delta neighborhood where you stay negative. So this is the same, right? G of x naught is different from 0. Therefore, by theorems on continuous, by theorem on continuous function, actual limits that we have proved some lectures ago, there exists some positive number delta such that g of x is different from 0 for every x belonging to x naught minus delta, x naught plus delta. Alright? So that's very important because it's telling me that the function h of x that I want to study, okay, is actually defined on an interval containing x naught. So that's important because you see, it's kind of, I'm saying, well, I have a function which is different from 0 at a point, okay? And now I look at the ratio. But who is telling me that this ratio is defined in an interval containing x naught? Do you see my point? So I just know that, I mean, from what it's written here, without using theorems or something, I just know that the ratio of f and g is definitely well defined at the point x naught, right? But how do I know that it's defined on an interval containing x naught? Because that's important. If it's not defined at an interval containing x naught, I don't have the definition of differentiability. Again, remember that the definition of differentiability is if g of x is defined on an interval I which contains the point x naught, okay, then you say that it's differentiable if there exists a limit. But when you speak about differentiability at a point, you're talking about functions defined on intervals containing that point. Okay. So before I before even starting writing down what this thing I want to prove, statement 3, even before writing this down, I should have discussed for you the possibility, okay, of expecting this function to be differentiable. And definitely, in order to expect that the function is differentiable, I first have to check that the function is defined on an interval containing the point. Because if it's not defined in a whole interval containing the point, then there is absolutely no reason to start thinking about is it differentiable or not. So, again, since our assumption is that g of x naught is different from 0, and that g is differentiable at x naught. Being differentiable, it will be continuous. Being continuous at x naught, with a value different from 0 at x naught, it turns out that for some delta positive, g of x is different from 0 at every x in x naught minus delta x naught plus delta. Okay? Which in turn implies that h of x is well defined on x naught minus delta x naught plus delta. So it makes sense to ask if it's differentiable there. Okay? So when I write down the incremental ratio of h, I'm sure that writing this thing down makes sense for every x delta close to x naught, provided delta is suitably small. So if you want, this remark that is written here would have been the premise to statement 3. If you don't premise that, I mean, you cannot even talk about the statement you want to prove. Okay? Do you see my point? I mean, that's again, it's not such a deep remark, but it's something you want to keep in mind. Okay, so what do we have here now? We have now we know that the question makes sense, and we have written the incremental ratio, right? And by the chain of algebraic identities, we have checked that this incremental ratio, let me copy all this thing up here. This is just f of x over g of x times g of x naught times g of x naught minus g of x over x minus x naught plus 1 over g of x naught, and here we have an f of x minus f of x naught divided by x minus x naught. Okay, that's, I've just copied the thing I had down here. Okay, so you don't need to write it again. This way I can freeze it. So, well, I don't know, this makes sense, and I know that since f and g are differentiable, f and g are continuous, so f of x and g of x differentiable at x naught implies they're both continuous at x naught, right? So these thing here, f of x is going to f of x naught, g of x is going to g of x naught. So this guy here is going to f of x naught over g of x naught squared. Alright? You just add 2 of the g. So this guy, what is the limit of this guy?
0.
Minus g prime of x naught, except there is a minus, right? Because be careful, the incremental ratio is flipped. Okay? So this guy here is going to minus g prime of x naught, while this one here is going to f prime of x naught. So all in all, this thing, as x goes to x naught, is converging to f prime of x naught over g of x naught, which is the second factor, minus f of x naught g prime of x naught over g of x naught squared. And that's the quotient, right? Usually you see it written like, you're more familiar definitely with that, right? If you like it more like that, it's the same thing. It's just okay.
So how come in the previous group for 1 and 2, we don't have to worry about whether gx will be, whether hx is well defined?
Well, because it's trivially well defined, right? I mean, when you, so in the first case, it was just a constant times f plus another constant times g. So provided g and f are defined, you don't need to ask that this is different from 0, this is different from 0, right? So this is like saying 3 times f of x minus 5 g of x. Or even when you take the product, right? If you have two functions that are defined, the product function is defined. There is nothing. But when you define the ratio, there is this operation of taking the ratio of g, which makes sense only if g is different from 0. So that's what brings a requirement, an additional requirement into the proof, right? Okay? Other questions? Okay, if not, let me now go back to this remark, right? So, the remark that if f is differentiable at the point, then it's continuous at the point. So the opposite thing is false, okay? So there is plenty of continuous functions that are not differentiable. Actually, you can even construct, it's in the end rather easy, a function that is continuous on an interval, is continuous on the real line, and it's not differentiable at any point on the real line. Okay, these things are not that difficult to construct. But let me just give you a simple example, the example you should keep in mind to be able to say that continuity doesn't imply differentiability. So, remark. Continues at a point x naught does not imply differentiable at x naught. Okay? So the example is you take f of x to be the absolute value of x, which is this thing. So take the absolute value of x. So my claim is that f of x is continuous at x equal to 0, but f of x is not differentiable at x equal to 0. So how do you check these from the definitions? Okay, the continuity is quite easy, right? I mean, there is actually not so much into it. But One is continuous, two is not differential. So how do we prove one? So given that f of 0 is equal to 0 by definition, right? The absolute value of 0 is 0 by definition. So what you want is that for every epsilon positive, there exists delta positive such that if x minus 0 is less than delta, then absolute value of x minus absolute value of 0 is less than epsilon, right? That's what it means, what it would mean for the absolute value to be continuous, right? I'm just writing down the definition of continuity for this function at 0, but that's trivial, right? So given epsilon, you just pick delta equal to epsilon, and you're done, right? Because the first line, so this is equivalently saying, equivalently you're just saying that for every epsilon positive, there exists delta positive, such that if the absolute value of x is positive and less than delta, then the absolute value of x is less than epsilon. Right? Because the absolute value of 0 is 0, and the absolute value of the absolute value is the absolute value. So it's really just a stupid thing. But this is definitely true. You just pick, you pick your delta to be an epsilon. Right? Given epsilon, you have to choose delta, you are going to choose it so it's exactly equal to epsilon. And the thing goes. Okay, this was very easy. So to check that the absolute value is continuous doesn't require any effort. Okay, how to check that we don't have differentiable functions. So let's check that you pick x different from 0, right? And you start writing down the incremental ratio, which is just this. So that's the incremental ratio of a function at 0. Now I plug in the fact that my function is the absolute value, right? So since I have the absolute value, here I have modulus of x minus modulus of 0 divided by x minus 0. So you notice that 0 is equal to 0, and you have the absolute value of x over x, right? And this thing is equal to 1 if x is positive, and minus 1 if x is negative. So the limit as x goes to 0 from the right of the incremental ratio of the absolute value at the point 0 is equal to 1. But the limit as x goes to 0 from the left of that same incremental ratio is equal to minus 1. So f prime of 0 cannot exist, right? Because if f prime of 0 exists, what it means? It means that the limit exists. But if the limit exists, then it has to coincide, then the limit from the right and the limit of the from the left must be the same. So the fact that they don't agree just immediately tells you that you cannot expect the limit to exist. Okay? So you can go one way, but you can go backwards. Okay, so now there is another important basic rule of, I mean, as you see, I'm not giving any geometric interpretation of the notion of differentiability, right? I'm just assuming that you have already seen that the derivative is the tangent to the graph of the function, blah, blah, blah. So these things, I think they have been taught to you in calculus classes, right? So are you all familiar to a certain extent with the geometric definition of the derivative? So here I'm just going through the formal aspects of it, right? I mean, how you prove these things that in calculus you have not been taught. And actually, as you see, they could have been teaching you these things, I guess, right? I mean, it's not that that difficult in the end. It's just a matter of getting a bit of terminology and of mind setting to understand, the right mindset to understand this. But I don't think it's really particularly difficult. So now let me show you another result. Which is called the chain rule. So first of all, what is the composition? So that's another aspect of defining function. So that we have a function f of x which is defined on an interval a, or an interval, sorry, r. Then we have a function g of the variable y defined on an interval j. So here I and j are intervals. Okay? And pretend to know that f of x belongs to j for every x in I. So whenever I compute the values of my function f on the interval I end up taking values in the interval j. So here is my interval I. This is f of x. And say that this is say this is the interval j now, and x, y, y, z. Now this is the interval j, and this is my function g on y, right? So given that the values of f on the interval I end up into the interval j, and that the function g is defined on the interval j, I can always compute g at f of x, right? So computing g of y at y equal to f of x makes sense for every x in the interval I, right? It's a well-designed machine. So for every x in I, compute f of x, I end up in j, and g is defined at every point of j. So I can compute g of f of x. It's automatic. I can do that. Okay? So I set h of x equals to g of f of x for x belonging to I. So this new function h is a function defined on an interval, and it's called the composition of f and g of f into g over the interval I, right? So that's the composition of f into g. Okay? So this is usually denoted by the function h is usually denoted as g circle f. Okay? So in books, the composition is denoted like that. When you see something like g circle f, it means that you're computing g at f, or otherwise say that f is composed into g. All right? Now, I mean, we have a very natural question, right? I mean, assume that f is differentiable at a point, x naught, and that g, so g will then be defined at f of x naught, right? But assume that g is differentiable at f of x naught. So is the composition differentiable at x naught, right? That's the chain rule. So if f of x is differentiable, not just defined, but differentiable at x naught, and g of y is differentiable at y naught equal to f of x naught, then h of x will be differentiable at the point x naught, and the derivative of h at the point x naught will be computed as g prime at f of x naught, right? G prime I can compute it at x naught, f of x naught, times f prime at x naught. So the quotient rule is just a particular case of the chain rule, right? Where you use the reciprocal function 1 over y, and you compute it at g of x. So you could have directly skipped the chain rule, but I mean, kind of stepping into this thing. One step at a time. So that's the chain rule. So you're all familiar, of course, with the chain rule, right? But you may have not seen the proof, and the proof is actually a nice exercise with the definition of limit. Now, there is something you have to be careful with, right? Because there is somehow an easy proof of the chain rule, which is wrong. Well, it's wrong. It's not so easy to justify. So, what is the easy proof? And then what is the real proof? So if you want the heuristic argument. So the heuristic proof for this thing is just to say, well, you want me to check if h is differentiable, so let me write down the incremental ratio. That's definitely something you want to do also in a formal proof. So you want to start writing down the incremental ratio of this guy, right, at x naught. So you start writing down this thing. Okay? And that's going to be the case even in the actual proof of the theorem. Okay, so you start writing down what is h of x minus h of x naught divided by x minus x naught. Okay, and then now, and that's the tricky point, now I want this f prime to pop up, right? Which means I want an incremental ratio of f at x naught to be written here somewhere, right? So I have a half of it, but I missed the numerator. So I just multiply and divide by f of x minus f of x naught, right? So if I do that, I got an f of x minus f of x naught divided by x minus x naught. And here, since I have multiplied by this guy, I have to divide by 2. So here I need to put f of x minus f of x naught, and here I will have my g computed at f of x minus g computed at f of x naught. And that's pretty much the proof, right? Because now, you see this guy, f of x minus f of x naught divided by x minus x naught, that's exactly what I know well, right? I mean, that's just an incremental ratio of f. This is going to f prime of x naught. Right? Okay, what about the first guy? See here, I have g computed at a point minus g computed at y naught. Okay? And here I have that very same point minus y naught. This very much resembles an incremental ratio, right, of g. So if you want, this whole block here, you could have written it as g of y minus g of y naught divided by y minus y naught, and computed at y equal to f of x, right? Do that? That's what it's written there, right? But now you see, as y goes to y naught, we all know where this goes, right? Where does it go?
And g prime of y naught.
At y naught, right? So as y goes to y naught, this ratio goes to g prime computed at f of x naught, which is what we want, right? We want this thing to appear. Now we are not taking exactly that limit, right? But we are taking y is equal to f of x. So as x goes to x naught, y equal to f of x goes to y naught equal to f of x naught, right? Because being f differentiable at x naught, it's also continuous at x naught. All right? So it's like, as x goes to x naught, this thing goes to y naught, and therefore, this whole chunk here goes to g prime computed at y naught, which is what I want. Okay? That's the heuristic argument, and the only defect I find in it is that I am multiplying and dividing by this f of x minus f of x naught, right? And so I should in principle worry if, I mean, what happens if x takes the value x naught, f of x naught infinitely many times when x goes to x naught, right? It's not exactly clear that I can do this. Because say that my function f of x looks a bit like that, so this is x naught, and this is f of x naught, right? Well, if my function does something like that, it oscillates many, many times around f of x naught, then, I mean, when I write this thing, I will have many, many points where this thing is actually 0, and I cannot divide. Right? It could be even worse, right? I mean, my function could be like, it goes here, and then it stays constantly equal to that for a while, for a whole interval. Then it detaches from that and stays constantly equal. Then it detaches constantly equal, and so on. So it could be that even this thing is not just a point that it's equal to 0 for a sequence of points. It could be 0 for a sequence of intervals that shrinks towards x naught. So this proof is definitely nice, but in the end, it leaves you the impression that you have not really proved anything, right? So you can fix it, and the way of fixing it is this, is just writing it down in a slightly more formal way. So, and it's again based on the remark. So the remark is that f of x, now let me pick a generic function, f of x is differentiable at x naught, that f of x minus f of x naught is equal to phi of x times x minus x naught for every point in your interval I. So let me put some, and put the interval, right? Notice that this is true, right? Because if you are in an interval I, but you are not x naught, well, that's just the definition, right? Phi of x is equal to that, so I just multiply everything and find the, right? And at the point x naught, that's also true. Because at the point x naught, the left-hand side is equal to 0, clearly. And the right-hand side is 0 times phi of x naught, which is defined, it's just a value. So it's 0 times an r, so it's 0. So that's definitely a truth. Okay, so if you're differentiable, there exists a continuous function such that f of x minus f of x naught is equal to phi of x times x minus x naught. Do you agree with that? Okay, let me take this very simple remark, okay, and formulate a theorem out of it, which is called the categorical criterion for differentiability, which is a very large name, but it's actually just this quite simple idea. Okay, so we'll leave it after category, which was a Greek mathematician. So f of x, the differentiable at x naught belonging to an interval I, if and only if there exists a function phi of x, which is defined, continuous at x naught, such that f of x minus f of x naught is equal to phi of x times x minus x naught for every x in the interval I. And the proof. One implication is the remark, right? So One implication is just our remark, right? I mean, the fact that if we are differentiable, we can define phi of x like that, and we have indeed found a continuous function of x naught such that that identity holds. So that's just the remark. And the opposite implication, so I want to show you that if I have a function f defined on the interval I, and I can find another function phi of x with this strange property, then my function f of x is differentiable. Well, but that's alright, right? Because all I'm saying is that the limit, as x goes to x naught, I want to compute this limit, right? The limit of f of x minus f of x naught over x minus x naught. Well, if I want to compute that, and I am in the assumption that I can find this function phi, well, since phi gives me this identity at every point in the interval, I can write the incremental ratio of f as phi of x. But by assumption, phi of x is continuous, right? So its limit at x naught is just its value at x naught. So if a function with this property exists, then it's true that f is differentiable, and its derivative is phi of x naught. Okay? So this tells you that thus f of x is differentiable at x naught with f prime of x naught equal to this function phi of x, phi at x naught. All right? See what time is it? Okay. So that's this catenary theorem. And how does it enter the chain rule? I will do that because it takes really 1 second to put the chain rule with this little criterion in mind. So what is now the actual proof of the chain rule then? Well, by the catenary theorem, right, when we say that f is differentiable at x naught and g is differentiable at y naught, so proof of chain rule. So by the catenary theorem, there exists phi of x defined on I and continues at x naught such that f of x minus f of x naught is equal to phi of x times x minus x naught, and there exists psi of y defined on J continues at y naught, and such that g of y minus g of y naught is equal to psi of y times y minus y naught, and the value of phi at x naught is the derivative of f at x naught, and the value of psi at y naught is equal to the derivative of g at y naught. So I just plug everything together and I'm done. Because what I'm going to do is simply to say, well, then what about the composition? Well, when I have g of f of x minus g of f of x naught, okay, these I can always divide it by x minus x naught. Okay, these I can write. So let me apply the property 2, the one with psi, and those values, and here I get psi of f of x times f of x minus f of x naught divided by x minus x naught. Okay. If you want, I can apply. I mean, here actually you wouldn't need to introduce the function phi in this theorem. So, but if you want, you can really kill. So you don't really need this chunk. You can throw it away. Feel free of throwing it away. Okay. I mean, it's not that it's not true, but it's not needed. So, and because once you're right here, right, this is converging to f prime of x naught without needing to use the phi for f. So this guy is going to f of x naught, which is our friend y naught, and psi of y is continuous there, right? So that this whole chunk here, psi at phi of x, is converging to psi at y naught, which is just g prime at y naught, which is our friend g prime at f of x. That's it, okay? And that's the proof of the chain.